Hello everyone. So we already have discussed different sensor parameters. So in the last lecture we have covered what is response and recovery time and then drift. Before that we have covered different other sensor parameters that are important for sensor design and sensor fabrication. Now we will start sensor physics. So just to give you a brief idea what we discussed in the last lecture, we have seen that what is response time and what is recovery time. Response time is something, or response recovery, both these parameter is related to the temporal response of a sensor. Temporal response is the response of a sensor with respect to time, and then we have seen that response and recovery time both are not interlinked, they are independent. And then we also have seen what is drift, how drift affects the sensor response. And today we will start with a basic concept of capacitive sensor, and for the sake of the completeness of this discussion, we will start with simple capacitor. You probably have read about capacitor in previous courses in 12th standard or in college as well, but let us start with the concept of capacitor so that we can connect our capacitive sensing concept well with a capacitor discussion. So a capacitor is nothing but a device that can store charges, and one of the simplest way to start the discussion of capacitor is to consider a parallel plate capacitor. What is a parallel plate capacitor? Parallel plate capacitors are when you have two different metal electrodes separated by a dielectric, that acts as a parallel plate capacitor. Now the electrodes can be made of metal or can be made of any other conductive material for that matter. These are different consideration, but as far as the capacitor discussion is concerned, we will consider that both the electrodes are made of metal. So you have two metal electrodes. This is a side view of the parallel plate capacitor. You have two metal electrodes and then you have a dielectric in the middle. When this arrangement is not connected to a voltage source, there is nothing in between these parallel plates. So the electric field is equal to 0. This is an unbiased condition. Now say you have connected these parallel plates with a voltage source V. The moment you connect the voltage source with that parallel plate capacitor, you will find that charges, different charges, positive and negative charges, will start getting stored in those parallel plates. And because of that charge separation, because you have positive charges in one direction and negative charges in the other direction, so you will get an electric field inside that capacitor. Now if you increase the applied voltage, the charges stored in those parallel plates will also increase. That means charge Q is proportional to V, applied voltage, or you can write Q is equal to a proportionality constant into V. This proportionality constant C is known as capacitor or capacitance. So your expression for C is equal to Q by V, that is what is given over here. So if you apply more voltage, you will find more charge in the plates. For an arrangement where the value of C is higher, you will find for same voltage you have more charges stored. What I mean by that is, if you are C, for example, say Q1 is equal to C1 into V, Q2 is equal to C2 into V. Now, if your C2 is higher than C1, for same applied voltage V, your Q2 will be higher than Q1, right? So, capacitance is something which can determine what is the amount of charge that will get stored in your parallel plates in this arrangement, right? Now, this capacitance is proportional to the area of the electrode. If the area of the electrode is high, more charges will get stored in those plates. So, it is proportional to the area. At the same time, this capacitance will be inversely proportional to the distance. If we increase this distance d, that is distance between the parallel plates, you will find that the capacity of storing charge will decrease. Why? Because your electric field will decrease. Electric field is nothing but your applied voltage by D, right? So, if your D is high, your E will be less. If your E is less, applied electric field is less, so less charge will get stored, right? So, it is inversely proportional to D. And at the same time, if the dielectric constant of this dielectric is higher, then again charge storage capacity will increase. So, if I combine all three of these, you will find that capacitance can be given by epsilon 0, epsilon r, A by D, where your capacitance is proportional to A, inversely proportional to D, again proportional to epsilon r. Okay. So, epsilon r is the relative static permittivity or dielectric constant of the dielectric media. Epsilon 0 is the dielectric constant of vacuum or say air. Okay. So, this is the expression for capacitance. Now, if you want to make a sensor out of this capacitor arrangement, you have three different parameters that you can think of. So, the first parameter is the distance. Say in a parallel plate capacitor, if there is some input or some stimuli that can change the distance between these two plates, then capacitance will change, and then that capacitance value can be calibrated with the stimuli. This is one way. The next way is the area. If we can change the overlapping area of these two electrodes, what I mean by that is, for example, if two electrodes are placed like this has a area A, this also has a area A, then you have certain capacitance. Now, say due to some stimuli, the overlapping area changed. Now, say this is a fraction of your A is overlapping with a fraction of your other electrode, right? So, if we can if you have certain sort of stimuli that can change the alignment of the electrodes, that also can be calibrated with the change in capacitance. And third is the dielectric constant. For example, if you have a stimuli that changes the dielectric constant of the dielectric material in the middle, then it will change the capacitance. Then again the capacitance can be calibrated with the input or the stimuli. Now, in this regard, here three different arrangements are shown. In the first arrangement, your top electrode is smaller than the bottom electrode. In such a situation, your electric field distribution will be something like this, where you will find that at the edges of your top electrode, the electric field is not straight, it is like bit bent. Okay. So, this is one consideration of capacitor electrodes. The second consideration is if your top and bottom electrode both are of same size. In that case, throughout the capacitor you will find that your electric field distribution is straight. And third is if your top and bottom electrodes are misaligned. Even if they are equal, they are misaligned. In that case, in the edges you will have this type of electric field distribution, and we may take advantage of these different electrode arrangements. How we can take arrangement? Let us see with one example. Say you have a arrangement where you have 4 different bottom electrodes, B1, B2, B3 and B4. Then you have a dielectric material in the middle, this one, and then you have a top electrode. Now the top electrode is partially creating overlap with all these 4 electrodes. Now if you start measuring capacitance between top electrode and B1, you will find there is a capacitance value because of this overlapping region. Again, the capacitance between top electrode and B2 will give you a result based on the overlapping zone here. Top electrode and B3 will give you a capacitance value based on the overlapping zone over here, and then you have again a overlapping zone between B4 and top electrode. So it will give another capacitance value between top electrode and B4. Now you have made an arrangement where the top electrode is kind of movable. So it moves once you apply force. In that case, if you apply a force in this direction as it is shown over here, you will find the overlapping zone that was there in this case, in the first case, will change. If your force is towards B1, then the overlapping zone towards B1 will increase. So the capacitance, say top electrode and B1 capacitance is C1, top electrode and B2 capacitance is C2, top electrode and B3 capacitance is C3, top electrode and B4 capacitance is C4. Now because you have applied a force on the top electrode and the top electrode is misaligned, it is a displaced condition. In that displaced condition, the C1 will increase, your C2 value may decrease, your C3 value will decrease, your C4 value may increase or decrease depending on in which direction you apply the force. Now just by taking these 4 values, you can calibrate what is the applied force, because the applied force will have a relation to the displacement. If the force is higher, the displacement will be higher, and if the displacement is higher, the overlapping zone will also increase. So there will be a relation to the displacement and the capacitance value, all 4. So in this way you can actually measure 3-axis force. If the force is in this direction, if the force is in this direction. So in all 3 axes, in x and y, at least in these 2 axes you will be able to measure. Even if you can change or if your top electrode is movable in the upwards direction, you can also measure the force applied in the upward direction, because then the distance between all these 4 electrodes will change. So that is how you can take advantage of the misalignment of electrodes in developing a sensor. So this is one of the examples where you can measure force based on the displacement of a top electrode, which in turn is giving you a change in capacitance. So fabricating this type of sensor may be helpful to develop a force sensor. Then let us see what is the effect of dielectric constant. So in order to understand this, what we have done is we have taken a case 1, say this is case 1, where we have a top electrode, we have a bottom electrode, and the dielectric in between the electrodes is air. So, we have taken air as a dielectric. In that case, the electric field E can be given by sigma divided by epsilon 0, where sigma is the charge constant, okay, or charge density, okay, and epsilon 0 is the dielectric constant of air, okay. Now, say you have replaced air with a new dielectric material. In that case, you will find there are a lot of dipoles that will be created because of the applied voltage, and these dipoles also will create a opposite electric field EP. So, initially because of the applied voltage, your electric field was E. Now, because of the applied dielectric material, that is because of the presence of dielectric material, you have a opposite electric field which is EP. Now, the effective electric field is E minus EP. So, the effective electric field now can be given by sigma divided by epsilon into epsilon r. Epsilon r is the dielectric constant of this new material. Previously, it was epsilon 0 because it was air. Now, it is epsilon 0 into epsilon r. So, you will find that your effective electric field is now sigma divided by the dielectric constant, that is epsilon 0 epsilon r, and hence the dielectric capacitance due to dielectric material will become epsilon 0 epsilon r a divided by d, right. Previously, it was epsilon 0 a divided by d, but now you have a new dielectric material in the place of air. So, it is now epsilon 0 epsilon r a divided by d, right, and this epsilon r is the dielectric constant of the new dielectric material. So, if you use a dielectric material that has a higher dielectric constant, you actually can increase the capacitance without changing the arrangement of the parallel plate capacitor. Now, in this direction, you can also take advantage of the dielectric material. For example, you want to make a sensor and you figured out there is a dielectric material A, and the dielectric constant of this material changes with temperature, right. So, if you use that capacitor in different temperatures, you will find different capacitance value, because at different temperature the dielectric constant epsilon r will change. If epsilon r is changing, your capacitance also will change. Then you can calibrate the capacitance with the dielectric constant, and then the dielectric constant can be related to the temperature. So, ultimately you get a calibration curve between capacitance and temperature. So, that is how you can utilize dielectric constant also for developing a sensor.
So, as we have seen, what is a capacitor and how this capacitor works, which is very basic, at least in case of a parallel plate capacitor, and we have seen what are the parameters that actually affects the capacitance value, because C is equal to epsilon 0 epsilon r a by d. Then we have these three parameters in our hand, which actually can be changed, and accordingly the capacitance also will change. Now, if we can attach, or if we can kind of interlink one of these parameters with any of the physical stimuli, be it temperature, be it humidity, then in that case, that particular physical parameter also can be detected just by looking at the change in capacitance, which we can check using an electronic system. So that is the whole idea. So the idea is, for example, if you have an epsilon r of a material, say A, say for a material A, the dielectric constant is epsilon r. Now, the epsilon r value changes when humidity, say, is changing around this particular material. So say the humidity is rising near the material A, and you observe that the dielectric constant of material A with the increase in relative humidity is actually decreasing. Just giving you an example. Now, in that case, relative humidity has a relation with the dielectric constant of that material. So let us assume that the dielectric constant of that material changes linearly with humidity. Say it's increasing. So if it is decreasing, then it will be something like that. So there is a linear relationship. Okay. Again, this epsilon r also has a relation with capacitance. Now say at 20% relative humidity, the value is 10. At 30% relative humidity, the value is 20. So now if you calculate the capacitance, then it will be k into 10. K is this value, which is fixed in case of the capacitor, epsilon 0 a by d. This value is fixed, and then you have epsilon r. So say this value is k, and then epsilon r value you put. So your C1 is k into 10, your C2 is k into 20. This is capacitor capacitance for 20% relative humidity. This is capacitance for 30% relative humidity. So you have now change in capacitance based on relative humidity. So that is how you can design a sensor. Now in this case, uh, your sensor is based on the change in epsilon r, and you are, what parameter you are changing, you are actually, what parameter you are detecting, you are actually detecting the relative humidity. So this is one way of designing the sensor. And then the other way we just have discussed, that if you can change the position of one electrode in this arrangement, then the capacitance value will change, because anyways the a effective a, that is the cross section area associated with this capacitor, will change. If the arrangement is this, you have certain capacitance. If the arrangement is this, then only this area is coming into the picture for the capacitance. So that is why, just by changing the position also, you can detect a certain physical parameter. So once it is based on deflection, usually force can lead to a deflection of electrode. So you can detect force uh, in terms of capacitor. So you can design the entire sensor in a way that your one electrode is fixed and the other electrode is deflecting. We have seen that example, but here what I'm trying to mm, argue is that sensor designer can decide based on the parameter or based on the stimuli what parameter we should actually target. We can target epsilon r, we can target effective cross sectional area, we also can target the d. For example, if you press from one side, you may find that this particular electrode come closer to the other electrode. In that case also your capacitance value will change. So you can also take advantage of the same. However, in all the cases, you need this capacitor arrangement, because the capacitor can directly be connected with a system, an electronic system. So electronic system cannot measure a physical quantity directly, but indirectly you can make this electronic system measure the physical quantity just by attaching a capacitor arrangement, which is actually translating the change in the physical parameter or the stimuli into an electrical parameter, that is capacitance. And same goes for a resistive sensor as well. So if you have a material which actually the conductance changes, say you have a material and the conductance of that material changes with relative humidity, and then if you connect this with a, say, voltmeter or a multimeter to measure the resistance, you'll find that the resistance is changing with relative humidity. Say if it is 10, the relative the resistance R is this. If it is 20, the resistance R is this. If it is 30, the resistance R is this. Then using this particular arrangement also, you can measure relative humidity. So relative humidity can be measured using a resistive setup as well as a capacitive setup. Now you have to decide which setup is more applicable for your application. And in both the cases, you may find that the sensitivity value, the range, the linearity, and the parameters that we have discussed previously are different. And based on that, you may decide that whether to go ahead with a capacitive sensor or to go ahead with a resistive sensor. So with this, what I would like to say is, a sensor designer himself or herself can design the sensor the way he or she wants. But one thing that you should keep in your mind is it also depends on the fabrication process. However, theoretically, you know, creating this relation is not very difficult. Anybody can mathematically design the sensor or theoretically design the sensor. In fact, in a simulation software also, with finite element method analysis, you can design the sensor, but you also have to check the practical feasibility of that sensor as far as the fabrication is concerned. You may come up with a design which in practice is not possible to fabricate. In that case, it doesn't matter even if your sensor is okay in the theoretical domain. In practice, you probably won't be able to make that sensor. So you also have to be very much careful about the practical feasibility of the sensor. So these different aspects actually will help you in designing different sensor, at the same time to think towards that direction, whether to go ahead with a specific structure for humidity sensor or not. For example, if you are talking about humidity sensor, then the material that is present as a dielectric in between these two electrode should come in contact with the ambient condition. Then only the relative humidity of the ambient condition can react with this uh, dielectric material and can create a change in the capacitance. But if the dielectric material is not coming in contact, or if the contact area is very less, in that case you probably won't be able to make that sensor. So you have to be very much careful about this, and then you can decide how to design the sensor. In this case, probably one option could be, if you have an electrode, say bottom electrode, then in the middle you have uh, dielectric material, and then the top electrode can be porous in nature, so that the humidity can go through that electrode and then can change the dielectric constant or interact with this material in the middle, and the corresponding change in the epsilon r can be reflected in terms of change in capacitance. So that is one way of designing the sensor. Just to give you an understanding, I have given this example.
So in the upcoming discussion, we will see different other capacitive sensing considerations, and we also will see different capacitor arrangements which can be utilized for developing sensors. Thank you.